All right, so I believe we're live. Hello, hello. How's everybody doing? Howdy doody. Is this actually taking me to the... I don't think it's actually going to take me to this stream URL. Me to this stream. Tweet this out. So that way that's a thing. Yeah, so welcome everybody. Let's try to keep it somewhat concise because we're going to, this is recorded, and I'd like to keep it kind of like, you know, people can, oh, okay. Oh, the chat, there we go. I'd like to keep it in such a way that people can come back to view the question later, you know, at their own time, their own leisure. All right, implement a trie, prefix tree. So I'll admit I've been kind of avoiding this question, thinking about it when I saw it last couple times. The reason I'm avoiding this question is, I don't know, it's a data structure, and like building your own data structure is always kind of like, you know, a little bit of extra effort, I guess. I don't really know. I don't really have a good reason, just that it's, and I haven't actually built the trie previously, so this will be my first time building my own trie data structure, so this should be interesting. So the idea behind a trie, though, if I remember correctly, is that it's like a tree that stores characters at each node, and you have partial matches to the prefixes of the character strings. That's why they call it a prefix tree, right, or a trie. So like if you wanted to match. Now I'm not sure exactly how it works. I guess you would match certain words. Yeah, I think that's how it works. So the idea is you would match, I believe it works like this. You have the root node is sort of like a null character, empty character. And then you could have the 26 characters come off of that root node as potential sort of next characters to match. So if you have it, or you could say, you know, n, maybe not 26, but like n, where n is the number of characters in the alphabet that you're working with. And then each of those nodes could have another n nodes branching off. And the idea is if you have something like apple, apple, and app, right? You may have insert search starts with. You may have you can basically match in the trie on those, or just apple and app, you can match on those two words by having an A character, then a P character that that's a child of a node for P that's a child of A, and then another child of that P that's a node for another P. And so anything that starts with APP, any words that start with APP, would then sort of follow down the tree from there. So like LE, you could have an L connected to the P and then an E connected to the L. Or if you wanted like applet, you could have a T even, or even a, what's the word? I don't know what words start with app. Apple, applet, appealing. Yeah, you could have the P branch off to an EALING, and appealing would be a word that would match, right? That would be stored in the trie. Now, what's interesting about this is the one way to implement it is, yeah, just a simple tree, basically. That, you know, the node has a character that it represents, and then children that are also nodes of the trie. And so I'd want to try node probably as like a subclass, not a subclass, an internal class, an inner class. And then you also, to show if it's search and insert, right, and also starts with, you can do a Boolean value in the node as well. So the Boolean would say like is basically is terminating character or something like that. If it's true, then when you reach that node, then you know that something stops there. So app, even though you've inserted apple, app would be present in your try, but it's not a terminating character at that second piece, so your search app should return false. So actually, this is a relatively straightforward thing to implement, especially if you're only inserting, searching, and checking things that start with, right? So starts with basically would just is there a node? Do you hit null or not when you search through these characters? So this is a pretty easy thing to implement, I think, overall. One question would be, how could you implement the same try with the same methods and then also implement a delete method as well? That's a good question. That's a very good question, because it's not clear whether or not actually that's not too hard. You can. No, that's not too bad. That's an interesting question. The way you do that, by the way, is I believe you'd use exactly this try I'm about to build, is that you would just check whether or not the parents are terminating nodes. So delete first. You would have to do a check that the search to find the bottom node of that, or the terminating node. And then if it doesn't have any children, then you can remove that node, but you also want to basically keep the parents in a stack, and then say, okay, is the next node a terminating node? If it's not, delete that one too, and you just keep doing that all the way back to the root. So that's pretty straightforward too, actually, believe it or not. That's actually not bad at all. You could delete from a try with relative ease, as long as you keep track of terminating node information. That's kind of nifty. Okay, so the way we're going to implement this, we're going to build a try. I have to remember C++ inner class, how that works. Nested classes, yeah. Nested classes, yeah. The name of the nested class exists in the scope and closing class. Name lookup for member. This is the scope and enclosing class. So any member of its enclosing class, nested class has access to all names to which the enclosing class has access, but it is otherwise independent and has no special access to the disappointer of the enclosing class. Yeah, it's pretty nifty. Declarations can use only type names, static numbers, and enumerators in the enclosing class. Declarations in a nested class can use any members of the enclosing class following the usual usage rules for the non-static members. So enclose, inner, so class inner, nested class. Okay, pretty nifty. For declaration definition. Obey member access specifier is a private member class, cannot be named outside the scope of the enclosing class, although those objects of that class may be manipulated. Pretty interesting. So you can do static nested member access. I want to say, actually I'm not sure. Yeah, that's what I was looking for, private public. Okay. So struct nested. Hopefully, I'm supposed to be off now, so hopefully my team picks that up. Or are they calling me directly? Hold on, let me see. Let me just make sure nothing's going on. Hold on, give me just one moment. Who's calling and why? Yeah, so we definitely want to, just give me a minute. This is kind of awkward. Whoever is watching this not live, I guess you would skip ahead a bit. Let me just see if that was for me and what it was, because that could have just been spam too on my phone. I just don't want it to be someone needs my help. and then I'm not there to help them. That would be very awkward. So kind of interesting. Yeah, so we'll do an inner class. So you can actually make I want to say a private class. That's kind of what I'm looking for. Public nested, pretty interesting. Yeah, I want to make it a private class. And that's just going to be the node class. So that's where all the fun stuff is going to happen. So I'll have a tree node, right? And it's going to be pretty straightforward. The members, we're going to have private members. We're going to say children, which is going to be use a vector for the children of tree node pointers. We'll use pointers. And you might want to think about who called me and why? Oh no, I have to. You might want to think about memory management too, which is kind of neat. I don't really do that too often. I'm wondering if I can use, in this case, use something special for my memory management, which is smart pointers. I would like to do that. That would be pretty nifty if I could get that going. Just give me a minute. Smart pointers. Smart pointers are great. Shared pointer. Or unique pointer. Yeah, because this is going to have, there's not going to be any pointers back to, yeah, I think we can use, I'm going to try to use smart pointers with this. I want to see if I can do this. Hopefully I do it correctly. Call me and why? No, that was just a spam call. Okay, yeah, it was right to my phone. It wasn't to, that wasn't to my yeah, it's really annoying. That wasn't to my, that wasn't to the office. Like I have an office phone, and then there's also, if you call the main office, it'll get a bunch of phones will ring, including mine, but I can see if it went to that sort of hub, or if it just went straight to my phone. That means someone called my phone directly, which is, you never pick that up if someone does that, because that means they're spam. Or they're just using it incorrectly. Like I'm not supposed to be exposed like that. They're sort of incorrectly trying to access me. Right, because obviously I'm off the clock now, as an example, right? And if they're calling me, they're supposed to be calling someone who's on the clock. Okay, so a smart pointer that returns shared ownership of an object through a pointer. Several shared pointer objects may own the same object. This object is destroyed on its memory deallocated when either of the following happens. So I want to use shared pointers for make shared, creates a shared pointer that manages a new object. I want to use shared pointers for this. Or even unique pointers. I feel like I need to read this again though. Remove that type exists, otherwise must satisfy nullable pointer. Deleter, constructor, new unique pointer. Returns a pointer to the magic object, releases the ownership. Reset, swap. Get swap. Override unique pointer pass through. Close file. Unique pointer next. Iterative destructor with long lists. Interesting. Runtime polymorphism. Demo. Custom lambda expression deleter. Interesting. unique ownership semantics demo, runtime polymorphism demo, custom deleter demo, expression. How do I use it though? Like I just, dereference pointer to the managed object. Okay. Assigns the unique pointer. Move reference pointer if that type exists, otherwise possessed. I haven't used these before. I don't really know what these do, how this works. I haven't used them very much. It's a smart pointer that owns and manages another object through a pointer and disposes of that object when the unique pointer goes out of scope. The object is disposed of using the associated deleter when either of the following happens. The managing unique pointer object is destroyed. Managing unique pointer object is assigned another pointer. Okay. The object is disposed of using a potential user supplied deleter by calling get deleter pointer. The default deleter uses the delete operator, which destroys the object and deallocates to the memory. The unique pointer may alternatively own no object, in which case it is called empty. There are two versions of standard unique pointer. So are unique pointers, do they dispose of themselves as well? So that's something I kind of wasn't clear on. Like, do you have to destroy those two? Because that kind of defeats the purpose a little bit. Class satisfies the requirements of move constructible, move assignable, but not the requirements of either copy constructible or copy assignable. Interesting. Two versions, manage a single object, manage dynamic allocated array of objects. Type requirements. Deleter must be function object or L value reference to a function object or L value reference to a function callable with an argument of type unique pointer. T delimiter, T deleter pointer. I don't fully understand that. Only non-const unique pointer can transfer the ownership of the managed object to another unique pointer. Any object's lifetime is managed by a const. It is limited to the scope in which the pointer is created. Interesting. Unique pointer is commonly used to manage the lifetime of objects, including providing exception safety to classes and functions that handle objects with dynamic lifetime by guaranteeing deletion on both normal exit and exit through exception. Passing ownership of uniquely owned objects with dynamic lifetime into functions. Acquiring ownership of uniquely owned objects with dynamic lifetime from functions. As the element type in move-aware containers such as vector, which hold pointers to dynamically allocated objects. Polymorphic behavior is desired. May be constructed for an incomplete type, such as to facilitate the use as a handle in the pimple idiom. Oh, interesting. The default deleter is used. So pimple idiom is a pointer, I think pointer implementation, something like that. Where does it go? Or Cheshire Cat idiom. The idea is that you have a pointer that points to the implementation of an object of a class. And it's basically abstracting away the implementation. So you have like, it's almost like a template, sort of, not a template or a interface. It's more like a lot like an interface. Experimental propagate const unique pointer widget pointer to implementation. Excuse me. Yeah. Is that what I said? Pointer implementation. Pointer to implementation. Removes implementation details of a class from its object representation by placing them in a separate class accessed through an opaque pointer. Right. So basically, you just have a pointer that points to another class. Which is kind of weird. Like, I don't know why. Yeah, it's used to construct C++ library interfaces with stable ABI and to reduce compile time dependencies. Right. Okay, that's interesting. So, yeah, take that for what it's worth. Basically, library interfaces, right? It's kind of neat. Kind of neat. Compilation firewall. Yeah. Another use case for the C++ core guidelines: do not over-parameterize members. Use a non-template core implementation to provide an ABI stable interface. Interesting. Yeah, okay. For example, following class template does not use the type T. Its private members are in the body of pushback. Yeah, templating can get you into kind of some funky territory. Access overhead, indirect through pointer, space overhead. Yeah, so there's kind of detailed explanation of, but yeah, pointer implementation in abstract. Right, it's like it's that simple. It's not. It's really not that. Not a particularly involved thing. So reset members of the primary template, unique pointer, special members of the specialization, unique pointer. Replaces the manage object given current pointer. The pointer that was managed by this performs the following actions. This order: save a copy of the current pointer. Overwrites the current pointer with the argument. The old pointer was not empty. Deletes the previously managed object. If the behaves the same as the reset member of the primary template, except that it will only participate in overhead resolution. New object to manage. To replace the manage object while supplying a new deleter as well. I'm wondering, do I really need to use a smart pointers for this? I would like to try to use smart pointers, but I'm not even sure if there's a reason to do it. Like a unique pointer, like it's very strange. Yeah, I don't know. Huh. I'm a little confused actually. I'm not even sure. What would be the destructor for a try? Like what do you even do? Internally, you're not going to be. Yeah, I don't know. I don't know. I probably should just write this without. What's memory management is really the thing that you're dealing with when it comes to destructors and whatnot. You don't want memory leaks. So when you create a try, you don't want to. I don't think I even have. Well, yeah. I don't know. We'll see. Hold on. We'll think about this. Think about memory management in a bit. We'll get back to it. I think what I should do is look at just implement this as I would normally first, and then see maybe there's an opportunity to make use of shared pointers or unique pointers. Let's do it that way. All right. So you're gonna have children. You're gonna have is terminating node. It's a Boolean. And then you're gonna have character, which character? Or just like the face or something, face character, something like that. The face of the node. And then have a constructor, default constructor, which is going to take Boolean is terminating node, or just call it terminating node. And then character, face character. Kind of need all of these things. Tree node. And these are going to just be, you can use initializer list for this. Which is, so we'll say is terminating node, whatever it is, right, true or false. I think character should come before Boolean. I don't know if that really matters, but face character, and then we'll say face character, face character. Make this nice, look nice here. Okay, so that's the constructor, and then we can add a child. Oh, this is kind of interesting. Huh. I almost want to make this a set rather than a vector. Because you would want to be able to remove children sort of randomly, I guess, potentially. Well, we're not removing any children at all, so we don't really need to. But if I wanted to be able to implement like deletion, I would want to add, I'd probably want those to be sets, actually. Interesting. So, we're not even going to implement deletion here, I think, at all. Like, at no point do we delete anything anyway, so this is kind of interesting. This is kind of interesting. So what methods do we need? We need add child, I guess, which should be actually, this is kind of also awkward. Like, this is not really. I'm using I'm mixing snake case and camel case, which I probably shouldn't be doing. Thinking about it. I like snake case for everything that's not names of classes. I use camel case for the names of classes. I don't know if that's confusing to people. I hope that's okay. I hope people don't mind that so much. It's kind of just my style. So add child. So we'll say, yeah, okay. Let's call it new child. It'll just be this children dot pushback new child. Pretty much. Just thinking. We can say update terminating status. New status. So that's if I don't know if we're actually gonna need that at all, by the way. That's sort of a setter. The reason you'd want that is you want the node I guess if you're using deletion, I don't know if we'll even need that either. I'm not sure that's even necessary either. Huh. Pretty interesting. I don't think we even need that. Terminating terminal, terminating terminal node. Huh. No kidding. Yeah, I actually think we should have a this actually shouldn't even be a should be an unordered map. characters of the tree nodes. Not thinking about it. Not really thinking about it. No, it's not really a it's not really a just an array. Although, well, no, actually, never mind. No. I take it back. I take it back. I have to find the child given a character, and that would be for auto x children, if x face character equals c, return x. Otherwise, return a null pointer. Did not find what we're looking for. Did I get this right? Children, face character, terminal node, tree node, face character, terminal node. A child, find child. Yeah, just do a simple linear search for the children. I think that's all we probably need for the tree node. Now, so insert a word. We're going to, so when we construct the tree, we'll have an initial tree node, which is going to be the head. And we'll set the head equal to a new trie node. Did I say tree node or trie node? Really should be a trie node, not tree node. Should be replace, right? Oh no, oh! That wasn't what I wanted. Isn't there a way to replace? Hold on, Firefox replace. Yeah, correct my. Oh, it's an add-on. That's annoying. Okay, I'll do it here then. Do I not have? Okay. There we go. Okay. It's pretty funny. Yeah. Anyway, trie node, not tree node, trie node. Okay, so head, new trie node. That's null character, I guess. So terminal node will be false. Face character is going to be null character, and the terminal node is false. It's not a terminal node, so we don't match empty. Well, actually, you could make it true, really, if you wanted to match the empty strings, but we're going to leave that out for now because they said that all inputs are guaranteed to be non-empty, so this could actually support empty strings. But yeah, okay. So inserts a word into the trie. We'll say so we'll say for auto C word head, or not head. We'll say trie node x equals head. Starts off with the head, or really. Yeah, that's fine, the head. And then we say, for each character in the word, we're going to say, find child of x. So we'll say trie node child equals find child of x. If not if child, then x equals child, else and we just want to say there's one more thing here. We want to make it the last node a terminating node. So actually we kind of want to do something like this. Find child. Oh, x dot find child is what we want. These are going to be publicly exposed. So child x find child c, if child, then set x to that child. Otherwise, we're going to set x equal to a new try node using face character and terminal node, right? So face character is going to be C, terminal node is going to be false, right? None of these are terminal nodes. And we're going to add the child to X. Oh, no. Oh, wait. So try node, new child. And then we're going to say X, add child, new child. You can actually construct the child right there, which is probably better. Nah, it's better to use the pointer, I think. Well, I kind of like this actually. This idea of like not exposing the pointer like that, but instead doing like this. You could do both, a pointer and like a constructor. I actually think the pointer is probably better. Yeah, pointer's better because you could always let's do it that way. Let's do the pointer. Yeah. So now, if there's a child, then you're going to set x to that child. Otherwise, you're going to create this new child and set x, add the new child, and then set x to this new child. So you're going to update this pointer, and then all the way at the end, we're going to basically run the same routine again for the last character, and we'll say character c equals word of word.size -1, or it would be the last of the back, I guess, word.back, something like that. Not sure if strings have a back. We could check that right now. String back. I don't know, I want to see. Basic string, yeah. It does have a back. Last character, okay. X find child. Right, so the head's never null. That's something important here. There's a child, set x to that child. And oh, and the thing is, yeah, I want to update this terminating status, right? We do want to update the terminating status then. Do want that mutator. true. It's true now. It's true. Now it's a terminal node. And so that's if you do find the child. Otherwise, you can create a new child and add that new child, and that's a terminal child, and then X is that new child. You don't actually really need X for this part because you're done with the loop at that point, but we'll keep it there just for the sake of it. All right, so that inserts the word into a trie. Turns true if the word is in the trie. So if it's in the trie, so we're not even worried about memory management at all here because we're never deleting this trie. Never deleting this. So, well, we can implement a deletion function at least, a destructor for the trie itself. The trie nodes won't. Well, yeah. So okay, we'll implement a destructor. Returns if the word is in the trie. So cert returns. Yeah. Okay. So what we would do is you do for. Or I guess a while loop really. Yeah, for loop. We could do for loops, fine. And it's going to be this trie node, which is X, which starts off at the head. And then we say, we could say int I equals 0. And we'll say I is less than word dot size, and X is not equal to end X, right? So X is not the null pointer. So both of these are true. Keep going if these are true. And we'll say increment I and set X to find child. Actually, this is a little confusing how we update X. So let's do it the other way around. Let's actually do the same thing we did here. Similarly to what we did here. Try node X equals head. For loop through the word. This time we go through the entire word. And we say C is word of I, then child is going to be X, find child. And then we say if. So let's say if not child, then we can return false. Otherwise, find the child. We update X equals child, and right, keep updating X to the child, and then finally return X. Getter and setter, right? His terminal node. Okay. So now, I want to test this. Search for the word, go through the whole thing, you get all the way to the end. So obviously, if the child's not found at all, then just return false, right? The word's not there. If you get all the way to the end though, then you want to check if it's a terminal node or not, because it might not be a terminal node. And that'll give you true or false. And then finally starts with is same, almost the same thing, same routine, except yeah, you just return true once you get all the way through. It doesn't matter if it's a terminal node or not. That's sort of the only difference. Okay, and then we want to throw in a destructor for good measure. So what we're going to do is really just call the head nodes try nodes destructor. how do you call it? Oh, you delete. Yeah. And it's no longer, you don't want it to be a dangling pointer either. Right? Point to nothing. Not try node. This is just the try. That's the try, and the try node. They call the heads to right, and then you have a destructor for try node, which is going to be recursive for each child, right? These will go out of don't matter. These will go out of scope with the children. You need to call each of their destructors, which becomes what? So each child, so you do for auto x children delete x, point x to null pointer. And it's recursive. I don't know if this really matters. I think this will actually recursively delete itself anyway. Like, I think that's sufficient, right? Because you get all the way down to some null pointers. And I think what'll happen is, let's say you get down to the leaves, right? On the leaf, there's no children to delete. This doesn't do anything. Yeah, I don't think this does anything, right? Like, I don't think this does anything. I think it just sets the pointers to null pointer, right? It'll call this recursively on the, so for the leaf node, it's actually right before the leaf node. On each leaf, this will get called, and this is gonna not do anything on the leaf node. Leaf node, this doesn't do anything. And then it'll set the pointer, this try node pointer, to a null pointer, which I think is going to free all of this memory then. And the vector, I think, will automatically deconstruct itself. I think vectors automatically, I don't think you have to delete vectors. How are the memory management of the vector class? I think that's automatic. It's pretty neat. Allocator is used to require release memory to construct, destroy the elements in that memory. The type must be the recordance allocator. What's this? What's the default allocator? Polymorphic allocator? What does that do? Class template, polymorphic allocators and allocators exhibits different allocation behavior depending on the memory resource which is constructed. Since memory resource uses runtime polymorphism to manage allocations, different container instances with polymorphic allocators, their static allocator type are interoperable but can behave as if they had different allocator types. All specializations meet the allocator completeness requirements. Allocate, deallocate, construct, destroy an object, and allocate storage. Polymorphic allocator does not propagate on container. Copy assignment, move assignment, or swap. As a result, move assignment of a polymorphic allocator using container can throw. Swapping to polymorphic allocator using containers whose allocators do not compare equal results in undefined behavior. As a result, move assignment of a polymorphic allocator using container can throw. Oh, that's interesting. Memory resource abstract interface for class that encapsulate memory resources. This is actually something I really haven't gotten too deep into my learning over time. I don't know, do you need to, my question would be, do I actually need to delete this? I think this will automatically deallocate. Once it goes out of scope. Once I take this pointer, I'm no longer pointing to it. This doesn't become, what do they call that? A memory leak. It actually just deallocates altogether. It's freed. not freed, but deleted. Yeah, because you only need to delete the new trie node, right? That's all that needs to get deleted is the trie node pointer that's created. Everything else is sort of allocated on its own. Object lifetime management, automatic exception safe. Allocators are class templates encapsulating memory allocation strategy. This allows generic containers to decouple memory management from the data itself. That is so awesome. That's so good. Memory resources implement memory allocation strategies that can be used by standard PMR polymorphic allocator, memory resource. For classes that encapsulate memory resources. I definitely need some more practice with these things, right? Like if I want to create my own data structures using these memory allocators. Synchronized pool resource. Pools of different block sizes, thread save, unsafe. Unsynchronized pool resource. Monotonic buffer resource. Uninitialized storage, raw storage iterator, get temporary buffer, turn temporary buffer, uninitialized copy. Range of objects to an uninitialized area of memory. Wow. Constrained uninitialized memory algorithms. Constrained uninitialized memory algorithms that accept range arguments for iterator sentinel pairs. Destroyed at, destroy end, construct at, declare reachable, undeclare reachable, declare no pointers, undeclared no pointers. Garbage collector support, wow. Interesting. Oh, that's interesting. Whoa. Whoa. Wow. Wow. That's pretty nifty. That's pretty nifty. I don't think I need to worry about the memory management of the vector. I think that's kind of the whole, yeah, the whole point of all this stuff, these allocators. That's awesome. That is such a burden removed from the programmer. I like to see that. All right. Okay, let's see how we do if we just run the code. Oh, of course. Yeah, this is a pointer, not a I forget what you call that. Yeah. Right. Non-static member must be called. Did you mean to call no arguments? Excuse me? Wait, what's wrong? Compile error. Update terminal status. Oh, that's what's wrong. I'm sorry, it doesn't actually need a pointer. Trie node x equals head. These are pointers. Okay. The word size. Oh. Prefix. Also, I would normally have this thing in here too, the standard string. And I probably would even want make these const references even. Just thinking, are any of these const? This is const too, I think. I don't think this needs a. None of this stuff is const. Yeah, these all get changed. you can actually mutate the terminal status. So, oh, it works. Hey, sweet. All right, that took a long time. That was like a full hour here. That's not really good. You kind of want to be able to do this in like probably 15 minutes. I guess. I don't know. I kind of did a lot of like poking around, looking at stuff, reading things. I don't actually know if this is also, I don't know if this is, I don't know if this is totally correct either. Let's just try some other things. Insert starts with search. Let's do zoo. Let's do another search too. Just do like a few test cases. Zoo, Apple. We can do apartment. When your apartment feels like a zoo. And then zoos. The thing is only said the zoo, the Z, Zoiks. Starts with Zoe. Starts with, let's do one that fails. Zoom. Search apartment. And then search Zoe, yeah, and then we can actually do another search for zoo. We should get, or just let's do Zoe, and then zoo, and finally we need to close this and put search there again. I'll do one more example, I guess, one more test case. Assuming, yeah, okay, it worked. Nice. I don't know. Insert. I don't know. It might take me a while to come up with another test case. Like what test cases could you even think of for this? Let me think. You have tricky cases. Insert search starts with, I mean, insertion's pretty straightforward. The search is, like I said, pretty straightforward. Starts with pretty straightforward. I don't know, man. I don't know what I could even be missing. This is like the hardest part when you're not sure what you missed. You're like, what are some tricky cases? If you have a bunch of children for the same node, maybe. We're not even deleting nodes, so it's kind of easy. I'm pretty sure we're good to go. Like, let's do like a few different children. 1, 2, 3, 4, 5. Let's do like 6 insertions here. Yeah, they said there's nothing's gonna be empty, so, and everything's gonna be lowercase letters, so it's pretty good, I guess. Overall, so 1, 2, 3, 4, 5, 6. I don't know. I don't even know. Do A, B, ABC, ABB, ACD, or AC. 1, 2, 3, 4, 5, 6. B, A, B, C, A, C, A, D. 1, 2, 3, 4, 5, 6, 7. Let's just add some words here. Agape, able, A, B, C, D, E, F, G, Abby, acting, basement, and adage. And then we'll say, so that's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. And then we'll do a few starts withs. 1, 2, 3, 4, 5. I don't know. Let's grab a bunch of random words. I don't know. Arbitrary. Adult. Actuary. Words, man, words. Actuary. Almost. Let's give one that we know is true. 8. Act. 1, 2, 3, 4, 5, 6. 1. Ooh. 1, 2, 3, 4, 5, 6. No. That's 7. 1, 2, 3, 4, 5. And then we'll do like a couple searches. Do like 3 searches. So basement we know is one of them. Base we know it should fail, and then adage should be another one. So we'll do 3 searches at the end here. Oh, we have 3 searches already. Okay. Did we get it all? I mean, did we get the form correct? Okay. All right. I don't know. If I missed something, I possibly missed something. Let's see what happens. I don't know what I. Oh, I got it. Oh, sweet. Nice. Nice. Not too bad. All right. So that concludes the try. How to construct a try node. That would take me a while in an interview. Well, again, part of it I was kind of like poking around with different possibilities with pointers and allocations and all that, which part of this was just kind of learning, reviewing how it's done in C++, containers in C++, and nested classes also kind of going over that again. Great. So let me go ahead and stop the stream. We're going to start a new stream with another problem.